Hi. So today we're going to talk about the slope field curve and how to guess a solution of a differential equation from the slope field. So I assume all of you can see this chapter over here, chapter 7.2. So this is one more method of kind of solving a differential equation using the graph. And I mean, it's kind of difficult to take notes here, so I'm going to just present from the chapter itself. So what is slope field? And how can you use it to actually guess the solution or the graph of the solution geometrically? So essentially, finding a solution is equivalent to finding the graph of the solution. So this slope field will help you to find out the graph of the solution. Let's look at an example. So let's look at the differential equation dy dt equals to t minus 2. Okay. So this is our differential equation, as you can see up here. And we will try to guess the graph of the solutions from this equation. How? Well, look at the left hand side. What does the left hand side tells you? So dy dt is essentially slope of the tangent at the point t to the graph of y at the point t, right? So essentially it is telling you that the slope of tangent at x coordinate equals to t is actually t minus 2. Meaning, for example, if we take t equals to 0, so t equals to 0 means this y-axis, right? So every point on this y-axis have t equals to 0. Okay, so this is a y versus t graph. So x-axis is actually denoted by t. So whenever I say t equals to 0, I actually mean this y-axis or this line, okay? Then if t equals to 0, the dy dt is 0 minus 2, which is negative 2. That means for t equals to 0, dy dt is negative 2. So it means no matter what your solution y is, the slope of the tangent at t equals to 0 will always be negative 2. Meaning if you draw the tangent, it would look like this small segment of line. So if you extend this very small little segment up here, as you can see this violet line, this very small little line segment has slope negative 2. And they have drawn so many small little lines everywhere, meaning that each of this line denote the tangent to the solution curve at t equals to 0. So you can understand there are so many solutions. There are infinitely many solutions to this equation. But no matter what the solution is, the tangent at t equals to 0 will always look like this, meaning the slope of these tangent lines at t equals to 0 will be always negative 2. Okay. Now similarly, if you take t equals to 1 instead of 0, the slope becomes, as you can see down here, the slope becomes negative 1, right? So if you draw this tangents, the tangents at t equals to 1 to the graph would look like this, right? So in this fashion, you are drawing the tangent line segments at t equals to 0, t equals to 1, t equals to 2, t equals to 10, and so on. So if you keep doing that for all values of t, you essentially end up having something like this. So let me just focus more on this diagram. So if you look this guy, so at t equals to 0, the slope is this, the tangent is this. At t equals to zero point 0.5, the tangent is this. At t equals to 1, the tangent is this. At t equals to 1.5, the tangent is this. At 2, it is this. Then at 3, 2.5, it becomes this. And then this, and so on. So the graph would look like, this, right? So actually, I think it's time for me to share screen. Yeah, I hope you can see the screen. So if I take this diagram, for example, the underlying equation is dy dt equals to t minus 2. So you can see that at t equals to 0, at this y coordinate, the tangent is a line of slope -2, right? So at t equals to 0, so maybe I should make a diagram, a table. So and so on, right? So you can see that a typical curve, so you start from here, then you go here, then you go here, then here, here, and so on. So a curve of the solution would look like this, right? Just by drawing this small tangent line segment, you can actually retrieve the entire solution. Or maybe actually I made a mistake. This should be here, here, and here. So the graph is something like this. Okay. And at this point, the slope becomes 0. And so on. I mean, you can draw this. This is one more solution. So I mean, this is a very bad picture. I mean, my drawing is very bad, but you can understand what's happening, right? It keeps moving from one square to the another and so on. So all these lines you see are the solution curve. So this is called a slope field. Essentially, using the differential equation, you record the slope of the tangent at every x coordinate t. And if you fix your t, you will actually get the tangent drawn to the all solutions at t equals to some point with slopes, right? Okay, let me stop sharing. So there goes slope field. I will solve a problem for you. But before that, let us also discuss what equilibrium solution is. So screen. Yeah. So okay, also let us define what equilibrium solution is. So suppose your differential equation is dy dt equals to some function of y. Then the constant function that a solution to this equation is called a equilibrium solution. Okay. For example, look at this guy. Dy dt is equal to, actually let me share my screen in the iPad. So at yeah. So let us consider this equation. Dy dt equals to -12 y minus 4, right? So notice that the function y equals to 0 and the constant 0 function is a solution. Okay, right? Because for y equals to 0, d dt of y, it's a constant function, right? So it is always 0. And half y times y minus 4, this is also 0, right? Also notice, not just 0, but the function y equals to 4 is also a solution to this equation. So meaning x-axis, y-axis. So if I draw this line is line y equal to 0, and this line, the line y equals to 4. These two lines represent the equilibrium solutions of the differential equation. So the function y equals to 0 and y equals to 4 are called equilibrium solution of the differential equation. Okay. In general, for a differential equation dy dt equals to fy, the function, it will be a constant function y such that f of y equals to 0 is by definition equilibrium solution. So equilibrium solution are all those constant functions y equals to c that are solution of your given differential equation. So all the constant functions that are solution to your differential equation are called equilibrium solution. So that's the definition. Okay. So now I'm going to solve activity 7.2.3 in front of you guys so that you have an idea of what's happening. So first, let's solve A and B first. So first question, make a plot of dy dt versus y on the axis provided. Looking at the graph, what values of y does y increase and for what values of y does y decrease? So, okay. Remember, if dy dt at t equals to a point A is positive, then y is increasing at A. If then y is decreasing at A. Okay. So let's see. So you want a plot of dy dt versus y. Okay. Now, so your new variable here is z, and z is negative half y times y minus 4. So what kind of graph do you get when you plot z versus y? You have seen this before. What kind of graph do you get when you plot y equals to negative half x times x minus 4? It's a parabola, right? Parabola that cuts at 0 and 4 with a negative side, right? So naturally, here the variables are kind of messed up. So it is not y versus x, it is z versus y. But the equation does not change, right? So it is going to be a parabola that will cut at 0. Let's see if I can draw it. No. That went surprisingly well. So this point is 0 and this point is 4. And this is the graph, right? This is the graph of dy dt versus y. It's an inverted parabola that will cut at y equals to 0 and y equals to 4. And actually, you don't need further more things to see when dy dt is increasing or not. So see, um, see from the graph, from the graph, notice that for y less than 0 or meaning on this side, right? So dy dt is negative when when y is on this side or y is on this side, right? I mean, look at the graph, like when y is here, the graph is negative, right? And as y keeps moving, the graph slowly becomes positive. As soon as y crosses 0, the graph becomes positive, and then as soon as the graph as soon as the y coordinate goes beyond y, the graph becomes negative, right? So notice that for y less than 0 or dy dt is negative, right? So meaning for y less than 0 or y greater than 4, graph of y is decreasing, right? Okay, also I should make some clarification here. Y is a function, right? What do I mean by the word y is less than 0? Well, given a function, you can still talk about whether it is positive or negative, right? Meaning, suppose I give you a function f. What does it mean that the function f is positive? It means the value of the function is positive or the value of the function is negative, right? So when I mean y less than 0 is what I'm trying to say here is that the value of the function y is negative. And if the value of the function y is negative, the graph is decreasing. Similarly, if the value of the function y is more than 4, the graph will be increasing. And it is irrespective of what solution to this differential equation you are choosing. So you choose a solution, call it y. If the value of y at some point negative, you can from there immediately claim that this function is going to be decreasing. Like starting from 0, if you keep going on the negative side, the graph will go down, and starting from 4, if you go more than 4, then the graph will like keep going decreasing. At the same time, also for y between 4 and 0, y will be increasing. So, meaning, suppose you take a point. So, meaning at a point x, if yx is between 4 and 0, then y will go up from x, or y will be increasing, y will be increasing at x, right? Makes sense? Now it's a very good question if you like thinking in this way. So I start with the point x. So this is, say, the graph of, so this is the x versus y graph, meaning I'm plotting a solution. So take a solution of the differential equation, I'm trying to plot its graph. So this is x, right? This is 4. And suppose that at x, the value of the graph, sorry, the value of the function y is between 0 and 4, right? So this is the point x comma yx. And you can see, right? You can see that this height of this point is actually between 0 and 4, right? And we just said that if the value of yx is between 0 and 4, the function will increase. So the function is increasing. Again, the value is still between 0 and 4. The function will further increase, further increase, further increase, further increase. Now our natural question is, this is the line. So this is the line y equals to 4, right? I know that the function, as long as the value of the function is less than 4, it will keep increasing. So the question is, will it ever become 4? Because if it ever becomes 4, you can see, right? Immediately, as it surpasses 4, it is decreasing. So it is increasing, 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 and suddenly it will decrease. That doesn't work. Do you see what I'm trying to say? Meaning that it will increase like this. Sorry, let me be more precise. It will increase. It will increase and say at x equals to x0, yx is 4. What happens after that? Well, see, then dy dt, why are you looking at dy dt? Okay. So I should have chosen, my bad. So I should have chosen, okay. So, okay, I have done a small notational mistake. The function is in terms of t, but I have chosen it to be x, but it doesn't really matter. So I should rephrase everything. So this is t. This is t. T, T. So say at t equals to, maybe say t equals to 5, y of 5 is 0, y of 5 is 4. Say, because it is increasing, right? We started from a certain t, y of t is between 0 and 4. We just said that the function will be then increasing at that t. So it is going to increase, and it will keep increasing as long as the value is less than 4. But at some point, it will maybe touching 4, right? I mean, it is increasing. So what happens when it touches 4? Say y of 5 is 4. Then what happens? Then dy dt at 5 is what? This is negative half y 5 minus 4. Right? That means dy dt at 5 is what? Y5 is 4, so it is 0, right? Now, what does it mean for the dy dt becoming 0 at the point 5? So, at t equals to 5, dy dt is 0. Now, as soon as dy dt becomes 0, it means the tangent is coinciding with the line here, meaning that the function is now constant. So there will be no change. So see, we started from a point, the value of y of t is between 0 and 4. That means it is increasing. It is increasing, 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 and then it touches 4, say at 5, right? But then as soon as it becomes 4, I mean the value of y becomes 4, dy dt becomes 0, meaning the function is attaining a constant state, meaning it will keep becoming 4 from that point and onward. But at the same time, this function is so-called differentiable. So for differentiable, it cannot happen that it suddenly becoming 4 and then becoming constant. Then this would be a point of discontinuity, or this would be a point of indifferentiability. So it means, so from t equals to 5 and onwards, y will become constantly 4. But t is differentiable, meaning this behavior, meaning this above behavior, that the function is constantly 4 from 1.5 and onwards, is not allowed. That is, you will have y not differentiable at t equals to 5, which is contradiction, because the function y is differentiable everywhere. So what is the moral of the story? Moral: y can never become 4. So what will happen to the graph of y? You all know what we call it. So if you draw the graph of y, You start from here. The graph of y will be asymptotical. So graph of y will increase asymptotically along y equals to 4. So this is 4. So it will grow very close to the line 4, but will never touch 4. Because you saw that as soon as it touches 4, you will have a different indifferentiability at that point. And that's not allowed because y is differentiable everywhere. So it will never touch 4, but it will keep increasing all the time. This is called asymptotic behavior. Okay? Sounds good? And similarly for something beneath is here. So if the value of our solution is beneath 0, you saw that it will keep decreasing, right? Here. If y is less than 0 at some point, that means it will keep decreasing. So it will just go away. Right? Meaning, okay, so let me be more precise. So I have 3 different solution curve. So this is solution curve or graph of a solution whose value at some point is between 0 and 4, right? So this is a solution whose value at some point is between 0 and 4, and we just saw that it will keep increasing, right? So if I try to complete it, it will be probably something like this. So on this side, it is asymptotically decreasing, and it is on this side, it is asymptotically increasing. So this is what a typical solution would look like. Typical solution would look like whose value at some point is between 0 and 4. So it is like once between 0 and 4, it is always between 0 and 4, but asymptotically. Now, about this guy, so this is, let me just copy and paste. This is graph of a solution whose value at some t is less than 0. This is number 2. And you can see, like, once less than 0, it will keep decreasing, and hence it will remain always less than 0. You saw that if at some point the value of the solution is negative, it will decrease from that point, and hence it will keep decreasing all the time. Because something smaller than negative is definitely a negative, a bigger negative number, right? On the other hand, if If at some point it is more than 4, it will keep decreasing, but again, asymptotically, right? So value at some t is more than 4, right? Because if the value is more than 4, as you have seen here, the graph will be decreasing, right? See this part, the y is decreasing, but again, if it touches 4, it will become constant from that point. But again, such like abrupt constant behavior is not allowed for a differentiable function. So it will never touch 4, it will never become 4, but it will be asymptotically equal to 4, right? Asymptotically decrease to 4. And then we have this two different function, y equals to 4 and y equals to 0. These two are so-called equilibrium solution, right? The constant equilibrium solution. So what did we learn from this? That there are two equilibrium solution and the other solution curve will kind of asymptotically behave around them. That's it. Okay. So I would expect you to spend some time around this. Now let me draw a slope field. So sketch the slope field, axis provided below. Recall that the differential equation is dy dt equals to oof, okay. Okay, how do you draw the slope field of this curve? Well, again, to draw the slope field, you need an idea of the tangent lines, right? How the tangent lines would look like. So here on the left hand side, the slope of the tangent is given to you, so that's good. On the right, some expression is given to you that will help you determine the dy dt. That is the slope of the tangent. So, okay, we'll do this. We will find out the dy dt for different values of y, right? So notice that I have drawn a bunch of points. Think for a moment, what is the common feature of all these points? See that all of these points have y coordinate 1, right? So this is y equals to 1, right? Now when y is 1, what is dy dt? According to the formula, it is negative half 1 minus 4. So it is 3 over 2. right? Meaning the tangent lines would look like this. So I'm going to, oh shit. So let me just do this. Actually, let me duplicate. So this is one such. So what does this line segments represent? So just for sake of uniformity, let me just copy paste these two things as well. Right? So what I have done, I have drawn a line of slope 3 over 2 or a line segment of slope 3 over 2. And at each point I have like created such a line with slope 3 over 2 because that's what the equation signifies, right? It signifies the slope of the tangent is always 3 over 2 whenever y is 1. Now, let us do it for y equals to 2. We're going to do the same thing. What is happening? So, all of this represent y equals to 2, meaning dy dt is what? It is 2, right? Just plug in here. Plug in y equals to negative 2 here. Or y equals to 2 here, right? So you will get, I guess, 2. So that means it is slightly more steep lines, right? So it will be something like this, right? Now, let me do the same business. Exact same business. Okay, and so. Right? Okay. I encourage you to solve these things, but then what I want to show you what happens at y equals to 4. So this is y equals to 4, and you can see dy dt is 0, right? That means what will happen? The we want a straight line. Have it. And so on. So complete this thing. So this is how you draw the slope field. At each point, you find out the tangent slope and then draw this small little line segment. And you can actually try to figure out the curve from here, right? So the curve would be something like this, right? Or maybe even steeper than that. Okay. So let me see if I want you to do any more. No, that's it. That's all about this section. So what I expect you to do, I expect you to solve a lot of problems, especially the assignments I'm going to assign right to you right now. And that would be all. Thank you.